Welcome to Brain Vision.
In this question, we have a source of sound and a detector that are a distance d apart, and a cardboard that is placed a distance root to d from the source and the detector as shown in the figure in the textbook. The source emits a sound of wavelength d/2. And we are told that it is found to be in phase with the direct wave received from the source once the wave reflects off of the cardboard. We're asked to find the minimum distance the cardboard should be shifted away so that the reflected wave becomes out of phase with the direct wave. So we know that from the source to the detector, that's going to be 2 wavelengths, right? Because the separation between the source and the detector is d. The wavelength is d/2. So that's 2 wavelengths separation between S and D. So in order for the wave that's reflected off of the cardboard that goes through this path to be in phase with the wave that's coming directly from the source to the detector, the green path has to be some multiple of the wavelength. Okay, in order for those to be, in phase with one another, the overall path, and actually maybe I'm going to write that over here, the overall length of that green path has to be n times the wavelength, n being some integer. So perhaps maybe 3, 4, 5, 6, we don't know. Okay, now in order for us to move the cardboard and get that these 2 waves would then be out of phase, we have to increase the length of the green path by half a wavelength. Okay, so we have to increase length of green path by half a wavelength. That's because then we would have the phase of the 2 waves are going to be completely opposite of one another, and so they're going to destructively interfere. Okay. So from this information, we can easily create an equation in order for us to solve for how much we're going to move the cardboard this way. So let's call that x. So I'm actually going to draw a new cardboard here just so we can see what that would look like after it's moved by x. And then we would have a new path of deflection that is slightly longer than the original path, and now hopefully that new path is half a wavelength longer than the original, and that's going to give us the destructive interference. Okay, or the completely out of phase. So what we want is for the old path, so I'm going to call the length of the old path SO, and the length of the new path, I'm going to call that SN. We want that to differ by 1/2 of a wavelength. So basically, I can create an equation out of that. So SN minus S0, that's going to be equal to 1/2 of a wavelength. And we know that a wavelength is equal to d/2, so we could perhaps substitute that in. So that would make this on the right-hand side d/2. d/4. Now I can write an equation for Sn and S0 based on what I know here. So let's see, the Sn or S, let's start with SO, and maybe I'll write it on the side here. That's going to be 2 because I've got 2 sides of this triangle here. So that's going to be 2 times, and then we'll just do a Pythagorean theorem. So the square root of d/2 squared plus the square root of 2 over d squared. Okay, and we can simplify this pretty easily, so I think I'm going to do that right away. Basically, what I did there is I just used a Pythagorean theorem on this, this triangle here. And then I'm multiplying by 2 because I have 2 hypotenuses to take into account with the full path. Okay, so if we simplify this, we're going to get square root of d squared over 4 plus 2d squared. So under this square root, that's going to be 9 over 4 d squared. And if I take the square root, I get 3 over 2. The 2's cancel, so that's just going to be 3d. Okay, so S0 is 3d. Sn, we know that it's going to be exactly the same calculation, but we're just going to have to increase that square root of 2d by x, whatever that x is that we're moving the cardboard by. So there's not too much we can do in terms of simplification there. I'm just going to throw that into the formula. So we're going to have 2 times the square root of d over 2 squared plus the square root of 2d plus x squared. And that's going to be all subtract S0, which we just found out is 3d. Yeah, 3d. Okay, perfect. So let's do some rearrangement. We need to find what x is here. So first thing, I'm going to pull that 3d to the other side. So it's going to be d over 4 plus 3d. 3 is 12 over 4, so that's going to be 13 over 4d. And then at the same time, let's divide the 2 out. So that's going to be 13 over 8 instead of 13 over 4. And then we'll just be left with the square root on the left-hand side. Next thing to do is obviously to take the square root of the whole equation. And I'm also going to apply the square onto that first term with the d. So that's going to be d squared over 4. I'm just going to leave this for now instead of expanding. It'll be much easier. And we're squaring, so that's going to be 169 over 64d. And let's see, so, d squared rather. And then we can bring the d squared over 4 to the other side. We know that we're going to have to make that over 64. So that's going to be 16 over 64 instead of 1/4. Oh, and that's going to be a minus. So 169 subtract 16. That is 153. So we get 153 over 64 d squared. And we've still got this on the left-hand side. We're going to take the square root of the whole thing now. So there's nothing really to do with the 153. That's just going to be square root 153. Square root of 64 is 8. Square root of d squared is d. And then we get root d plus x. So we just have to do one final subtraction. And that's going to give us the amount by which to shift the cardboard. And nothing much we can do with this in terms of simplifying. We could probably get it down to just one factor of d. But let's just do it numerically. So the square root of 153 divided by 8, it's 1.54. Subtract the square root of 2. So that gives us a movement of 0.13 d, which seems rather reasonable. So basically what this is saying is if we shift the cardboard 0.13 d, that's going to create an extra half a wavelength that that green wave has to travel, and that's going to create, it's going to make the red and the green out of phase rather than in phase. All right, so that is our final answer right here. And that's it for this question.